Have you ever wondered how do we hear sounds? So in this video, we will be discussing about how we hear sounds and what are the properties of sounds. So sound waves are vibrations that travel through a medium such as air, water and solid. Sounds are mechanical waves. That's why they need medium to propagate. It causes the air particles around it to also vibrate, creating a series of compressions and rarefactions that propagate through the air. It travels in longitudinal waves rather than transverse waves. So the everything that we studied was about sound and how does sound travel. So sound is a mechanical wave, meaning it requires a medium to travel, and light, for example, is a non-mechanical waves because it doesn't require any medium to travel, because we know light also travels in vacuum. That is why light can reach the earth from the sun, whereas sound requires a medium, either air, water or any solid. That is why we don't hear any sounds in the space or the outer space of the earth. Now let's talk about how sound creates these waves with an example. So the example is of a pair of forks, and what we do is make this fork vibrate. So when this fork vibrates, what we will observe is a series of compression and rarefaction. Now, when we say compression, we can see right there that com at the place of compression, there is a higher pressure because we can see all these particles at a very small space joined together, and in case of rarefaction we have these same air particles. These lines represent air particles, so these same air particles are spread across the air. Now we can understand compression is a place of higher pressure and rarefaction is a place of lower pressure. Now let's take an example. Now let's talk about this even more. So the fact is that when this happens, when this point vibrates, this vibration which occurs causes this series of rarefaction and compression. Now, how does it cause a series? The thing is, it is continuously vibrating. It doesn't just vibrate once and stops. It vibrates once, then vibrates again, then again and again and again. That causes continuous series of rarefaction and compression, and it vibrates till it reaches our ears. Now, for example, if it goes back, now let's take this fork, and for example, I plugged it, so it was something in this position. It was not straight, it was behind. So what was happening is more of the space was left and rarefaction was created. But when it moved forward, it struck the air, it struck the air, which caused a compression. And that's how a series of rarefaction and compression creates. When the fork goes backwards, a rarefaction is created, and when the fork goes forward, a compression is created. And it keeps doing this rhythmic motion, which causes rarefaction and compression to occur. Now, if we plot this in the graph, it would look something like this. This is the wave of sound plotted on a graph. Now, we also discussed a little earlier that waves travel in longitudinal waves. Now, what does sound travel in longitudinal waves? What are longitudinal waves? So, there are two types of waves. Longitudinal, we have waves of two types: longitudinal, and the second type is transverse. Longitudinal waves are those waves where the particles move in the same direction as the motion of the wave. Meaning, if my wave is going in this direction, then the particles will also go in the same direction. Just like in this case, where the motion of the wave is in this direction and the particles are also moving forward in the forward direction. Now, transverse waves looks something like this. Even though this is a graph of a sound wave, but you have to remember graphs and real life are different. Graphs are on a 2D figure, whereas the real life is a three-dimensional space. So that's why we represent uh, longitudinal waves in graphs is transverse, but this is how a transverse waves look like. The motion of the wave is in this direction, but the particles are moving upward and downward. It is something like what happens when you throw a piece of rock in water. The water spreads out and the particles of water moves up and down. But since this is just a graph, that is why we also represent the sound waves as this. Now let's talk about properties of sound waves. The first is frequency of sound waves. Frequency is the number of vibrations per second and determines the pitch of the sound. What do we mean by vibrations per second? Now let's expand this figure. So vibration or frequency can be counted by how many oscillations does the wave do in 1 second. Now what is one oscillation? If you notice, let's talk about some terms, which is the crest and the trough. Now if we notice in a graph, it is a linear and uniform graph where they are uniformly above and down. Now what this means is the highest point above, this horizon, this is horizon. This is the horizon, the middle part. This is the horizon. The highest part from the horizon is known as crest and the lowest part from the horizon is known as trough. And there are multiple crests and troughs as you can see in the figure. Now what is one oscillation? One oscillation is when it goes from here and then down and back up. What this means is the one oscillation is completed when the wave travels from one crest to another crest or from one trough to another trough, meaning it would travel from here, then it will go here, 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 and when it reaches here, this is one oscillation. From this point, from first crest to the second crest, this is one oscillation. Or we can go from one trough, which is trough 1 to trough 2. This would be also one oscillation. Now frequency says that the number of oscillations in 1 second is known as frequency. So for example, just like this oscillation, it does 20 oscillation in 1 second. It means the frequency of the sound wave is 20 hertz. We represent frequency in the terms of hertz, which is written as short form Hz. Hertz is written as Hz. So if it travels 30 waves, if it does 30 oscillations in 1 second, that means its frequency is 30 hertz. Now you can see that there is a huge difference between the crest, whereas in this case the difference is smaller, which means it will do more amount of oscillations in 1 second. For example, let's say it does 50 hertz. So it has higher frequency and this one has lower frequency. So we also should know that we have heard about girls having high pitched voices and boys having low pitched voices, or girls have a high voice and boys have deep voice. But the thing is, higher the amount of frequency, higher the amount of pitch. So girls have a higher frequency of sound than boys. That is why their voices are high pitched and the voices of boys are low pitched. Now let's talk about amplitude. So amplitude is a measure of sound waves intensity or loudness. Now this is the part of loudness. Frequency is not related about loudness at all. Frequency does not care about how the sound would actually sound. The loudness is measured by amplitude of the sound wave. Larger the amplitude, it will produce louder sounds, and smaller amplitudes would produce quieter sounds. Now let's talk what are amplitudes. So amplitudes is the difference from the horizon to the crest. In this case, you can see the difference between horizon and crest is very small. It is very small and hence it is a low amplitude. This is a medium amplitude and this is high amplitude. It will be a very small sound like a whisper. This would be a normal talk and this would when you are screaming someone's name. Now let's talk about wavelength, which is our final property of the sound wave. So wavelength is the distance between two consecutive compressions or rarefactions, or we also can say two consecutive crest and trough. Two consecutive crest and trough. Because while plotting it on a graph or while performing an experiment, we will usually use crest and troughs rather than compressions and rarefactions. So shorter wavelengths produce higher pitched sounds. What do we mean by higher pitched? By higher pitched, we mean higher frequency. I will just write F for frequency, higher frequency. While longer wavelengths produce low pitched, or and longer would produce lower pitched voice, meaning low frequency. Now let's understand with an example. Now here is our crest, and this is our crest too. So the difference between two consecutive crests is the wavelength, and we will represent wavelength by a symbol called lambda. And this is also a wavelength, which is the difference between two consecutive troughs. Now let's take an example where the wavelength is very small. Where the wavelength is very small, it would look something like this. Here the wavelength is extremely small, which causes higher amounts of frequency. Let's take this entire thing takes 1 second. It takes 1 second, and same in this case, it takes 1 second here as well. It takes 1 second here as well. So in this case, it will perform 1 and 2. It would be of 2 hertz. 2 hertz, because in 1 second it does two oscillations, whereas in this case it would be 4 hertz. So as you read, lesser the amount of wavelength, higher the frequency, and larger the amount of wavelength, lower the frequency. So this is the end of the video about sound waves and how do we hear sounds.